Welcome back, everyone. In this video, we're going to start Chapter 12 of the ebook, looking at the properties of gases and the kinetic molecular theory, and the implications that the kinetic molecular theory has in terms of the relationship between temperature of a gas, its molar mass, and its speed. So we've already looked a little bit at solids, liquids, and gases in previous videos in terms of their intermolecular forces and the interactions that exist between them. We're now going to delve deeper into the properties of gases. And gases are a collection of atoms or molecules that they will expand to fill the shape and the size of their container. They exert a force on that container that we call pressure. They tend to have very low densities and are compressible. And you can see here a kind of cartoonish depiction of the differences between solids, liquids, and gases. Gases, again, they will occupy whatever container they are in, and there's a lot of space in between the particles. The image on your screen does not actually do gases justice. There's actually much, much larger space in between them if the molecules were really that big. For liquids, these will fill the bottom of the container that they're in. They will mold to fill the shape of that container, but they don't occupy the entire volume. And solids have a very fixed size and shape. So what's going on the molecular level to give rise to these properties of gases? Well, it all has to do with intermolecular forces, or rather, the lack thereof. The kinetic molecular theory of gases describes how gas molecules are in constant motion. And there's 5 key postulates or assumptions of the kinetic molecular theory. First, we assume that all gas molecules are moving in straight lines and that their direction is random. We assume that molecules themselves are small, and the volume of the molecules is much, much smaller than the volume of the container. The molecules do not attract or repel each other. So in other words, all that we've learned about intermolecular forces does not apply to gases. And that's simply because they're so spread out that the interactions that would exist between them are essentially zero. When molecules collide, those collisions are elastic, or in other words, no energy is lost to the environment in terms of heat or sound. Now, we know that this isn't actually the case, but it's a good assumption to start with, especially when we deal with gases that we are going to term ideal. Then finally, the average kinetic energy is going to be proportional to the temperature of that collection of gas particles. And that temperature, of course, is going to be measured in units of Kelvin. So at this point, what I'd like you to do is pause the video and go to the link that's indicated here. You can also find these questions and the appropriate link to this in Canvas in the second link for this lecture page. So pause the video, read over the instructions here for this demonstration of kinetic molecular theory, and then come back. Welcome back. So what do we notice in this demonstration about the speeds of the helium atoms? Well, there's a wide range of speeds. And we also notice that the speed of any one molecule actually is changing quite frequently. Sometimes it's moving fast, sometimes it's moving slowly. As you decrease the temperature and then increase it slowly, what's happening? Well, as the temperature goes down, the collection of particles is slowing down on the whole. And as the temperature increases, the molecules are speeding up on average. However, it's important to recognize that there still is a distribution of speeds. So now if we add some neon particles, what you'll notice is that on average, that they're slower than helium atoms, but there are indeed some neon atoms that are moving faster than helium. Then when you reduce the container's volume, you'll notice that the speed distribution of both gases is actually unchanged, but the pressure goes up. So this is just depicting those 5 ideas that we demonstrated, that we talked about in terms of the kinetic molecular theory. Let's now talk more about pressure. So in the demonstration that you did, you saw something like this when you had your neon particles and your helium particles. And every time a gas particle hits the container's wall, it exerts pressure. Pressure we define as the amount of force that is exerted per unit area. Because of this definition, we can see that pressure and volume are indirectly related to each other. Pressure is also proportional to the mass of the particles and the speed at which they are going. Temperature is also related to the speeds of molecules. We discussed that one of the assumptions of the kinetic molecular theory is that temperature is related to the average kinetic energy. Therefore, when we look at a collection of gas particles, we can describe the temperature of the whole collection. We can never talk about the temperature of any one particle because temperature is related to the collective's average kinetic energy. So when you look at gas particles, we again saw that they're moving at different speeds. And those speeds follow a distribution that we call the Maxwell-Boltzmann distribution. What you can see here is that there is a lower limit. Here, the lowest speed that we can reach is, of course, 0. But you'll notice that at higher speeds that we don't taper off completely, even at this upper limit that's indicated on the screen. Because we can have ever increasing speeds, up theoretically until the speed of light, we see that the distribution is not a perfectly symmetrical distribution. It's slightly weighted towards the higher speeds. And so our average speed is actually slightly higher than the most probable speed. When we talk about the root mean square speed, this is approximately the average speed of the molecule. And this is somewhere off in this region, just slightly to the right of the peak. So let's take a look at some data and evaluate which variables are affecting the root mean square speed of a collection of gas molecules. I'd like you to pause the video and look over these data on your own and try to determine for yourself which variables are affecting kinetic energy, which variables are affecting RMS speed, as well as whether there's a difference in speeds for heavier versus lighter molecules. Welcome back. So what do the data tell us? Well, what we see is that the temperature is affecting the average kinetic energy. The average kinetic energy listed there on the far right-hand side, we see is increasing when the temperature increases. And in fact, it's a linear increase. So when the temperature doubles, so does the average kinetic energy. When you look at what variables are affecting the RMS speed, we see that temperature and molar mass are affecting it. So for the same two collection of gas molecules, at different temperatures, we see that the speeds are changing. Notice, however, that it's not a linear increase. Doubling the temperature does not double the root mean square speed. And when we change the molar mass, but keep the temperature constant, notice that our root mean square speed goes down. But again, it does not go down linearly. If we double the molar mass, it does not go down by half. And then finally, we do see that on average, for a given temperature, molecules which are heavier are moving slower than lighter molecules. So this, again, is showing us the relationship between temperature and speed. And the textbook goes through some detail in showing how to derive this. Fundamentally, this bottom equation here is the one that we need to be able to use. This tells us that the root mean square speed for a collection of gas particles is determined by taking the square root of 3 times the gas constant R times the absolute temperature in Kelvin over the molar mass of the gas molecules, and that needs to be measured in kilograms per mole. So the gas constant R is given here. Again, our temperature needs to be in Kelvin, our molar mass needs to be in kilograms per mole. And so what we see here is because of the square root factor, there is not a linear increase in the speed when the temperature increases, and there's not a linear decrease in the speed when the molar mass increases. All right, so let's see if you can utilize this equation. So determine the root mean square speed of nitrogen gas at room temperature. Pause the video and try this on your own, and then I'll walk you through a solution. Welcome back. So let's make this calculation. We have a starting temperature of 25 degrees Celsius. We need to convert that to Kelvin. The conversion from Celsius to Kelvin is done by adding 273.15 to the temperature in Celsius. The molar mass we can find by adding together the atomic masses of nitrogen. And we need to remember to convert this into kilograms per mole. The gas constant R is given in joules per mole per Kelvin. And the reason why we need to convert from grams per mole to kilograms per mole is because the unit of joule is actually a compound unit containing kilograms times meters squared per second squared. Therefore, when we take the molar mass, it's going to cancel out the units of kilogram. So after we plug in all our values, we want to, you should verify that the units do indeed cancel out. And we're left with about 515 meters per second. So here's another problem for you to think about. What would our distributions look like if we have the same identity of the gas, but the temperature is the variable? So you should be able to do this by thinking through the relationship between molar mass, temperature, and root mean square speed. So assume that each of these distributions is for nitrogen gas. Rank them in order of decreasing temperature. Pause the video and try this on your own. Welcome back. So we know that as temperature increases, that there are fewer molecules moving slowly and that there are more molecules moving quickly. We saw this when we did the demonstration earlier. Now, the RMS speed is indicated, in this case, by those black dots on the curve. And as the temperature increases, so does the RMS speed. Therefore, we know that the blue curve has the highest RMS speed and therefore must have the highest temperature. And the red curve has the lowest temperature. And in fact, if you were to determine the actual temperature by reading off the approximate root mean square speeds and calculating those in, you would see that we have about 100 degrees Kelvin for the red, 300 for the green, and 1000 Kelvin for the blue. All right, here's our last problem that I'd like you to try and determine. So you've got 5 gases shown here. We want to know what's the approximate RMS speed of argon at this temperature. Pause the video and try this on your own. Welcome back. So we know that if we're at a fixed temperature, molecules that have higher molar masses will tend to have lower speeds. We can use this equation to calculate the RMS speeds and also to remember that this relationship is the case. However, we don't actually need to calculate the RMS speeds. Because we know the identities of the gases, we can calculate their molar masses and then use the information about the molar mass to rank them. So we know that the heavier molecules will move on average at slower speeds, and the lighter molecules on average will move at faster speeds. So if we're looking at argon, we see that it's right about here. So if we go down to the x-axis, we can see that it's just below 500 meters per second, or in this case, closest to 432. That's it for this video. Thanks for watching. Have a great day.